Welcome back. This is a recap of what we worked on in class today. We were talking about free body diagrams. And a free body diagram is a diagram where we use a dot to represent an object, and we use arrows to represent all of the forces that act on that object. So if I had a force up, maybe I have the normal force of a table supporting an object, and the force of gravity pulling down. Maybe there's some tension pulling to the right, and if I had friction pulling to the left, I might have a free body diagram that looks like this. So this might be a situation if I have a mass sitting on a table and some tension pulling it down to the right. So looking at this mass right here, call it mass 1. My mass 1 here might have tension pulling to the right, maybe some friction pulling back. The gravity is pulling down on this block, which means that the block is exerting a force on the table, and that means, by Newton's third law, that the table must be exerting a normal force back up on the block. We know this isn't going to sink down in or bounce off the table, so these two forces must be equal to each other. Not because of Newton's third law, but because the block is not accelerating up or down here. So let's look at the example we looked at in class and see how we can apply this. We're going to look at the classic example that makes it clear how this thing works. We're applying Newton's second law to a system called an Atwood machine. The Atwood machine is a massless, frictionless pulley with a mass hanging on one side, a perfect massless, stretchless string passing over it, and a mass on the other side that might be different, mass 2. Remember, we want this pulley to be both massless and frictionless so that friction doesn't steal any energy from the system and so that it doesn't take any effort to rotate this pulley at all. So the pulley won't have any inertia of its own. So what does Newton's second law say? It says that the net force on every massive object in a system will cause some acceleration. But that acceleration will be inversely proportional to how massive it is. So if we write this as effect equals cause, we're saying that the acceleration of each object, say the acceleration of mass 1, will be the net force on mass 1 divided by mass 1. The same thing would be true for mass 2. So I could say the acceleration on object I is equal to the net force on object I divided by the mass of object I. So let's apply this to mass 1 here. I'll draw the free body diagram first. I know there's some tension pulling up and a force of gravity pulling down. The tension we'll call T, and the force of gravity I know is proportional to the mass and the acceleration due to gravity, which on Earth near the Earth's surface is about 10 meters per second squared. For the second object, I have the same tension. Why is it the same tension? Well, if the tension were different in different parts of the string, it would stretch or break. We have information transmitted instantaneously all along this string because it's perfectly stiff, can't stretch, and it has no mass of its own. These are all things we can add later. Stretchy string, string with mass, friction in the pulley, mass in the pulley. We can add those things one at a time, but let's keep it simple to start. Gravity's pulling down on this object and pulls down with a force m2g. Now the very tempting thing that I want to deal with explicitly is to say the reason that this will move, let's suppose mass 2 is heavier, then we know it would move down and mass 1 would move up, just based on experience and intuition. Intuition can sometimes be useful in physics, sometimes it's less useful, but if m2 were heavier, we know it would accelerate downward. So the tempting thing is to say that T over here is equal to m2g, but pulling up, because this is the source of the tension, right? So if we said that this free body diagram, we're going to put the wrong idea in the box here. The wrong idea would be that mass 1 has m2g pulling up and m1g pulling down, and mass 2 has m1g pulling up and m2g pulling down. So the reason these free body diagrams are useful is that they give us a way to determine F net. So in the y direction, the vertical direction here, let's put some coordinates here. We'll call this x horizontally and y vertically, the traditional choice. So in the y direction, for the first mass, mass 1, I would have m2g minus m1g. Why is it positive and negative? Because this one is up and this one is down. See, up and down. And that would equal the first mass times its acceleration. And then for the second mass, m2, we'd say that this is going to be up minus down, so m1g minus m2g, and that would equal m2a. So we can already see there are a few problems. One of the problems here is that I have two equations and my only unknown is a. You can't have two equations and only one unknown. It won't be a solvable problem in general. There might be special case solutions, but it will not be generally solvable. So let's take a look at what happens in this case. If we solve for a, I would get that the acceleration of the first object, I'm just going to solve this equation for a, is going to be m2g minus m1g. So let's factor out the g. m2 minus m1 g, all divided by, we're solving for a, so this would be divided by m1, and solving the second equation for a, it's the acceleration of the second object, that would be m1 minus m2, similarly factor out the g, divided by m2. And we've seen this can't be right because we know if the string can't stretch, the acceleration of this guy up must equal the acceleration of that one down. So let's suppose these were, say, 3 kilograms and 5 kilograms. Then I would have what? 5 minus 3 over 3 times g. So that's 5 minus 3 is 2 over 3, 2/3 times 10, 6.67 roughly meters per second squared. And here I would have 3 minus 5, all times g, over 5. So 3 minus 5, I'd have negative 2/5 g, negative 20/5, or negative 4 meters per second squared. And clearly these are not equal to each other. And that can't happen because they're connected by a string, so they need to have opposite accelerations. So this is just wrong. So let's see the right way to do it. The right way to do this is to use the tension that we identified. This tension is what communicates the force from one side to the other, but I can't simply say that this is the same as this, that m2g is the same as t, because t is the same everywhere. So let's watch it. Let's read off our actual free body diagrams. So now the right way. For mass 1, I see that I'm going to have T minus mg as the net force, T minus m1g, and that will equal the acceleration of that mass. Let's assume it's going to go up, which we know if these are 3 and 5, in fact, it will go up because it's lighter than this side. So that's going to equal m1a, taking a to be positive and up to be positive. Then for the second mass, we'll have T minus m2g equals m2 times its acceleration, and let's be careful. As I said, this is the most common place to make a mistake in this problem if you get this far. The most common thing is to not know where to start, which is fine, but we'll get past that. m2, and we're going to say this is the opposite acceleration, so minus a. Now, most students' first inclination is to solve these both for t if you're asked for a, and then just solve for a via algebra. My favorite method is to take a linear combination of the equations in order to eliminate one of the unknowns. So I'm going to take this second equation and subtract it from the first. So I'll have t minus t, and that will eliminate t. T minus t gives me 0. Negative minus m2 Two negatives gives me a positive m2g added to this equation minus m1g equals m1a minus a minus m2a. So that's a m1 plus m2a. So solving for a, I'll factor out this g, and I see that I have an m2 minus m1 over m2 plus m1 all times g. Several good things here. Mass over mass has no unit, so it cancels out, and g has units of acceleration, which is what I'm looking for, so that's good news. I also see that this expression is anti-symmetric in m2 and m1, meaning if I switched which one was called m2 and which one was called m1, I would get the same number, but with m1 minus m2, meaning I'd get the same number but negative, and I know that indeed is what must happen if we switched these with each other. What else happens? What if m1 equals m2, so the system is balanced? Then what would the acceleration be? Say 5 minus 5, it would be 0, which we also know is the case. Now what would happen if m1 were 0? Well, if m1 were 0, m2 would just fall to the ground with an acceleration of g. If we eliminate both of these, I have m2 over m2, which is 1, so that my acceleration would indeed be g. So this checks out all of those considerations. We considered the limits that the two masses are equal, the limit that either mass disappears. We checked the dimensions or units of the two sides, and everything looks good. So now if we were asked for the tension, how would we find it? Well, we would just take A, plug it into this equation, and solve for T. Let's do that. T is going to equal, notice I can move this term over to the other side as a plus m1g. So I'm going to have an m2 times the acceleration, which is m2 minus m1 over m2 plus m1 g, and add this term to the other side. So we have plus m1 times g. So that is an expression for our tension that we can plug in these numbers, and now we know both of the unknowns.